All right, I just turned on the recorder and we're still getting people coming in. Um, One question had been before I turned it on, am I still trying to get caught up with grading? Actually, I'm trying to get caught up with both printing and grading, and then also some caught up with getting things out there on Blackboard. So some things have been graded but not put on Blackboard. Other things have been printed but not graded or put on Blackboard. And then some things I haven't even gotten to print yet. So I won't have a lot of time this afternoon to do it. And unfortunately, we're going to be driving tomorrow when I usually have my office hours. So there's a good chance I won't get a lot. I'm going to get as much done this afternoon and evening as I can, and after that, and we're coming back Monday, so I will lose my 2 hours in the morning too, because we'll be driving back, and so it's going to be rush, rush, rush next week trying to get things caught up. I'm going to get as much as I can today, but we've got to pack tonight too because we're leaving very early in the morning. So it's it's a rush time, and sorry, things are not in better shape than they are. But finally, knock on wood, they've eased off a little bit all the requirements for us to do. So I'm sure there will be more. Okay, this is a very small crowd to get started. Oh, here comes Labrina. So I say that just as somebody else is coming in. Labrina is here. And let's see. Is that just the four of you? 1, 2, 3, 4. Yep. Got you. I saw you coming in, so I marked you before you got here. All right. Thank you for telling me. All right. Any questions, issues, concerns before we get going on today's? We are recording already, so anything that you want to bring up. All right. Just a little bit of review of where we are, where we're heading, where we've been, that kind of stuff. Okay. We're in chapter 23, and I didn't really get a good feel for how far we're in. I think we're probably more than halfway through the chapter. Okay. But even if not, we've got all day today to work on it. Okay. So we'll be on 23 the rest of the day. Okay. Now, if we finish early, which I think we will, then there'll be a time for you to ask questions or work on research papers. Okay, this class, I think I only have 1, 2 in so far. Now, maybe there's 1 or 2 others out there I haven't printed or graded, but not overflowing with research papers yet. And then I'm slowly catching up the labs and the tests, and so far it looks like a good number of you are right pretty much on track with that, which is good to see. But that will give you time this afternoon to work on research paper, work on labs, work on tests. Okay. And while y'all are doing that, unless you need my help, I'll be here available for you for any questions you may have on anything. But if y'all are going to work independently and you don't need me on, then I will be printing like crazy. I'm also going to be filing some because some of that stack I just showed you, like I said, it's already been graded. It's just I haven't had a chance to file it yet. So that stack will get smaller when I just get them filed with the rest of the class. Here comes Christian. Let me get him here. Okay. Christians here. All right, that gets us up to 5 students. So we do have enough for a basketball team now, but that's about all. Hope some more will be coming in. Yep, just 5 students so far. So today we'll hopefully wrap up 23. I think we'll have plenty of time to do that and probably have some time left over. And like I said, you can work on research paper, past labs, and past tests. Okay. And do that for the rest of the day. Now, starting Tuesday of next week, that's week 7, we will start chapter 24. Okay? We'll go for 2.5 hours on the 24, stop there, and then do the lab for chapter 23. I don't think it'll be a full 2-hour lab, but it is sort of a fun lab. Hopefully we can get that done within the 2 hours easily. Okay? Then on Thursday of next week, we will hopefully kind of wrap up chapter 24. If we don't finish it, we'll get the vast majority of it done. Now, we will hang on, and then for the following Tuesday after that, then we'll do the lab, and if we have any more chapter 24 to do, we'll do it, but I have a feeling we'll finish 24 by Thursday of next week, and then the last week we'll have the chapter 24 lab, and then I'll post the chapter 24 test, and I may go on and post the final exam as well, and that way you have the rest of Tuesday to work on the 3 of those. You have the rest, and by the way, the lab for chapter 24 is going to be largely on your own. I mean, there's nothing really I have to do to hold hands with it. There's no websites to go to and that kind of stuff. So that'll be mostly on your own, and also the test, both the chapter 24 test and the final exam. And if you can get those back into me by Thursday, I'll be here on Thursday. If there are any last questions, thoughts, issues, concerns, and I thought maybe we'd have pizza. I'm just kidding. I mean, I wish we could, but we'll be separate. But maybe we can all bring a slice of pizza and enjoy it together. I don't know. I'm just kidding. Okay. Any questions then on how we're going to wrap things up? Okay. I do have it right that the mini term does go through next week. Now something is happening I just lost Zoom. People. I see 5 people. How many do we have? Yeah, we still only had 5. So I guess now my internet still looked good. It wasn't as strong as it was this morning, but I guess there are storms in the area. At least there's plenty of rain in the area, and some places that could be accompanied by a good bit of wind too. So I don't know why, but that happened. So let me go back. Can y'all hear me now? Because I could hear you. I've got to get everything set up that I had moved around before. I got to move it back. Yeah, I'm up to 4 bars. For a while there, I went down to 3. Let me make sure my internet is still, yeah, I've still got good internet access. And now, James, you're in the way. I got to scoot you to the right. Okay, got it done. And let's go back to the current slide. All right. Any questions of how we're going to wrap up the term? I guess my question that I was asking when we lost everything is, Jackson is coming in. Let me get him here. Jackson's here. Okay, my question to you, I am correct in that we do have my internet connection is unstable, so I'm going to quit talking. Well, did I get broken up there? Or was that all clear what I was saying?
Yes, sir. You're breaking up.
Okay. Yeah, the internet connection, I had a sign that said internet connection is unstable. So what I usually do then is I just start talking about other stuff rather than the class, okay? Just so you can hear me talking to tell me whether we were actually breaking up or not. And breaking up is hard. No, that's an old song. Okay, we've lost the slide we were on, and I can't get it back yet. It'll come back, I'm sure. Okay. All right. Now, again, I'll try to ask. Maybe I should quit asking this question. It seems to knock us off every time. Um, it is correct that we go through Thursday of not next week, but the following week. Is that right? I haven't checked, but that's 8 weeks, and I just assumed they were had not cheated us any days there. So we'll have class today, Tuesday and Thursday of next week, Tuesday and Thursday of the following week. So that last Thursday is basically y'all bringing stuff up, letting me know if you have any problems, questions, that kind of stuff. I think we'll be through with everything to do in class on Tuesday. We'll wrap up everything on Tuesday, and Thursday will just be a day I'll be here. And if no one's here, I'll be grading papers like crazy. If y'all do show up, then I will answer any questions you have. Sancho is here, so let me get him in.
Okay, Mr. Fowler, I just wanted to confirm. I know you said that if we make a bad grade on a test and it helps us to drop it, that you would drop it. But was that the same for labs?
Yes, you get to drop one lab and one test. The lowest lab, the lowest test, if it helps your grade. Um,
Okay, so
and
if
most
you
of the
do not
time,
do a lab,
say,
you drop.
say again.
Okay.
Okay, I cut you off there. I
I was
didn't mean to.
saying if I do not do a lab,
Yeah,
if I do not do a lab, then it could be just dropped, right?
that will be dropped. Exactly. Right. Right. And but wait to make those decisions till you see all your lab scores to make sure you don't want to. Hey, I think I can do better on this one. Um, so yeah, don't be hasty in making that cut. All right. All right. Any other questions before we get going on weather forecasting? Now, I keep seeing some chats. Are they coming up or what is this? Let's see. I've got, I think, 7 students here. Let me make sure nobody's in the waiting room. They're not. And let me make sure I got 7 on the roll book. 1, 2, 3, 4, 5, 6, 7. Yeah. All right. We haven't broken double digits yet, but let's go on and get started, unless there's other questions. All right. I'm going to scoop my everything over just a little bit because my book is almost about to fall off. Again, chapter 23, weather and climate. We're right at the end of the weather part, and something keeps popping up. Are these chats? Are any of them things I need to be responding to? If they are, please go on and say. What's that?
It's not for you.
Not for me. Okay, fine. Um, it's just that I have so many things open to open those to, and especially if it's something you don't want viewed. If I open it on this, then it's going to show up on the recording. So I want to make sure that you want it open before I open it. All right, so we're right at the end of the weather part of the chapter, and this is the last slide on that, and then we'll get into the climate part. So any questions on weather so far? And let's see, that's more chats. Okay, I guess. Let me just make sure I don't have anyone in the waiting room. No. Okay. All right, weather forecasting. This has evolved during my lifetime for sure. Okay, and I would say probably you've noticed some very major changes in your lifetime as well. Now, you probably don't remember the weather when you were really small, but or I hope you realize things are way, way better now than they used to be. In fact, I can remember my father was a farmer, and he had the Farmer's Almanac. So anytime that he was wanting to look ahead anyway, he went to the Farmer's Almanac, and all basically things were they based everything on what the weather patterns had been over the previous however many years they had been publishing or getting information on it, and then just basically predicted what they thought was going to be happening now. Very much a backward looking type of thing, and definitely nothing that you could send to the bank. Okay. Now, the weather people on TV probably had a little bit better stuff to do. Uh, they basically were looking at what's happening to the west of us, and depending on how fast those systems were moving, they could predict when those things would probably get to us. Again, just pretty good guesses, and that was about it. And Darius is coming in. Let me get him marked. Okay. Now, with the advent of computers, okay, let me make sure that's not somebody else coming in. I think it's just a chat. Okay, we should have 8 students here. I've got 1, 2, 3, 4, 5, 6, 7, 8. Got it. Okay. With the advent of computers and computer modeling and all kinds of different radars, okay, if you go and watch the weather, especially when it's severe weather, and you see those weather stations. Well, let's pull up the thus and so model. Let's pull up. Oh, here's somebody else. Here's Kendra coming in. So let me get her marked here. Okay, that gets us up to 9 students here, I believe. Yep, that seems right. And there are a bunch of chats going on. I hope that's all it is, that I don't have many people in the waiting room.
Darius Robinson said, don't forget to check them in.
Yes, I got him. I got him when he was, yeah. Okay, got it. Thanks. Appreciate it. And feel free, folks, to so on and say things. I mean, I don't get upset, wiped out, or anything else if I'm talking and you say, did you get me in? I'll be glad to say, sure I did, or no, I don't want you here. No, I won't say I won't want you here, but whatever. Okay. Who's this? Jackson. Yes, I did. Yep. So yeah, I've got 9 students here so far, and that's all the ones that the thing indicates that we got here. So I've got you all in the books. Okay, we're talking about weather, and for those who came in late, we're in chapter 23, weather and climate, and my internet connection is unstable, so I'm going to quit talking about physical science. Okay, did I break up some there? It said my internet connection was unstable. Are y'all still with me?
Sounds good right now.
Okay, good. We're in chapter 23, weather and climate, and if we can finally get through this last slide on weather, we'll be into the climate side of it. So, with the advent of computers, modeling, modeling goes with the computers, radar and other ways of doing things, weather forecasting has gotten tremendously more accurate, more precise, further out there, you might say, but still there's a long way to go. And whether we can ever get there, here's the problem. It's based on mathematical models of our atmosphere. That's the first point here. Now, what in the world do we mean by that? We have an atmosphere that goes for miles and miles and miles upward. And that atmosphere is split into, I would say, at least 7 different, what you might call zones. 7 different areas that have very different temperatures, very different wind speeds, very different amounts of ionization. I mean, there's just so much difference and variation in our atmosphere. And the thing is, it's not fixed zones either. One day it may be, one zone may be thick, another day it may be thin, and another zone thick, So things are always, always, always changing in the atmosphere. Well, we can't measure everything in the atmosphere. We are very limited. I think they send up what they call weather balloons, maybe 2 or 3 times a week at most, And what those things are, they have instrumentation on them, and they go up into the atmosphere, sending data, radio signal back to the base, letting them know what the temperature, the elevation, the temperature, the wind speed, the relative humidity, all the things that they can measure as they go up, constantly sending that back, and then at some point it's gone. It falls back to Earth, whatever, but usually it's gone. I don't think they can retrieve them. So they're expensive, not super expensive, but they don't do it 2 or 3 times a day. I'll put it that way. They're too expensive for that. And maybe not, things don't change that frequently, but they do change. So number one, our input. Are any of your computer science majors? No. In the old days, here was the common saying in computer science, in computers in general. You probably have heard it. Garbage in, garbage out. Ever hear that? GIGO. Garbage in, garbage out. If you feed the best computers with bad information, you're going to get bad results. Well, it's not that they feed them with bad information, they feed these models with limited information. So that's the first thing about the model. We have limited input, only so much. Now, the weather station also, weather system, and for the country, it's National Oceanic and Atmospheric Administration, or the National Weather Service. They work together. National Weather Service only has so much resources, okay, so they can only do so much. But they do have some planes that do fly around. I talked to you last time about my friend who had been a hurricane pilot and flew into hurricanes so they could collect data there. They do have planes up there flying periodically that they collect data in that part of the atmosphere. Now that's not the upper parts, but it goes pretty far up. They also, and this is something I'm not too sure about, but I'm pretty certain that certain of the airlines and other aircraft, maybe I'm guessing postal aircraft or things like this, they probably have relationships. They send them back data. So they're getting data all the time. I'm not sure it's all that much useful. It's probably measuring the same thing over and over. Where we already know what's going on is where we don't know. That's what we don't know. So anyway, the mathematical models are based on limited input. Okay. Number two, they're models. Okay. They are not exact. They just go by basically historic or mathematical equations that may not actually fit the real situations that well. Okay? There may be one set of equations that really do well with wind speed, but don't really do well with, say, temperature or relative humidity or something like that. But then if you focus on that, you lose some of the precision somewhere else. So mathematical models are just that, models. And if you've ever listened to the weather on TV or maybe anywhere, they'll say, well, this model that says this, but this one says this. I tend to go somewhere toward this one. The different models give us different information, different predictions. That's tough to deal with. Now, even with the limited data we have, we still have a lot. But because of the complexity, all the things that are changing there are billions of calculations that have to be made in that model that goes up for miles, and of course thousands of miles this way to get the whole country in here. If to get the whole world is just unbelievable, but just to get your area of the country and enough of the surrounding so you can make some good predictions, billions of calculations are needed. So therefore they have to use supercomputers, and supercomputers are not cheap. Okay, I know there's a supercomputer up in Huntsville. I am assuming that some of the weather stations are borrowing time or buying time off that supercomputer, but they can't use it constantly, so they make their predictions maybe once or twice a day or something like that. Now here's a statement that sort of makes me grin. Now this is an old slide, and maybe things are better than this now, but it says weather forecasting is fairly accurate not accurate, but fairly accurate forecast up to 3 days. And yet, what do they post every day on the weather? Here's your 7 day outlook. Well, guess what? Anything beyond 3 days is kind of wishful thinking. Educated guesses for sure. Better than no guess at all. But 3 days, and that third day, probably there's a lot of the confidence intervals are growing bigger and bigger every day. Now, maybe, because I said this is an older slide, maybe they have it up to maybe 4 days now. But I can almost guarantee you the 7 day forecast. I really have wanted to do this sometime. I've never taken the time to do it, to record what they say the 7 day forecast is today. And then tomorrow, look at the 6 day. And then the next day, look at the 5 day. And the next day, look at the 4th day. And then start looking at D321 and see how much change happens in that 7 day forecast before it actually gets here. I bet you it's very, very different from reality. Unless you have one of these patterns that nothing's changing. Middle of summertime, it's going to be hot. Okay, that's probably pretty good. Now, here's the major uncertainty. I've given you all this insufficient technology. Not that the supercomputers aren't good, they're really good. Insufficient data, yeah, maybe that's more so. But here's the big thing. The technology to connect small scale events to large scale events. Okay? In other words, what does this temperature change or this wind speed change somewhere up in the stratosphere, how is that going to affect us a day or two from now? Okay, that's a really tough thing to predict because there's all sorts of other things happening in between that. So a lot of uncertainty, a lot of uncertainty. And then this is almost a lead into the next chapter. Ultimately, the oceanic influences need to be better understood. We actually probably do understand the atmosphere above us, even though we have big gaps there, better than they do that enormous body of water. Something like 72% of the Earth's surface is covered by oceanic water. Okay, we don't understand those influences nearly like we should. For instance, on the east coast of the U.S., we have the Gulf Stream. We know what it does. It keeps our ports open. It sends warm water up to even as far as Ireland and England. It's just a tremendous thing. We probably understand that better than we do some currents, but there's currents like that all over the ocean that are making huge changes to weather that we don't fully understand how these things work. If any of you have ever listened to the weather and they start talking about El Nino and La Nina, okay, those are oceanic influence happening off the west coast of South America, somewhere off Peru or Chile, somewhere out there in the ocean. Something's going on there, and when certain things happen, we know this is going to happen several days later here. Why that happens? Okay, we understand when it happens, this is going to happen. We can predict based on that, but we don't know what's going to happen out there next because that's something we don't understand. What is the driving forces making El Nino happen, making La Nina happen? How serious or severe La Nina or El Nino will be, or how weak and ineffective it'll be. We don't know. How frequently it's going to happen? Well, maybe about every 7 years or something like that, but that's not very precise. How to connect small scale to large scale events, especially when those involve oceanic influences. That's a problem. So have your salt shaker so you can take weather forecasts with a grain of salt. Now, I promise you, they're tons better than they were when I was young, okay? But they still are not up to 7 day, I guarantee. Okay? Now, I can't advance the slide till I click on it. Here is climate. This turns the page to page 588. And why in the world this is a major section change, I don't know. Weather forecasting was 23.3. Climate has nothing well, it has a little something, but it's a whole new topic here. This is the second half of the book, of the chapter. What do we mean by climate? It's a composite, larger weather patterns occurring over, when they say number of years, they're not talking about 3 or 4 years. They're talking about decades, centuries, millennia. Okay, I think it's Asher coming in. Let me get him marked here. I believe that's him. I'm having to go all the way across the page here. And by the way, I don't know if any of you knew or know Deja Gray Miller, who was in the class. She's no longer in the class. I do know she had, I believe it was a surgery earlier in the term, and she had missed a lot. And I don't know if that's the reason she decided not to come back, or hopefully it wasn't anything worse than that. But anyway, if y'all did know her, she's no longer showing up on the roll. Okay, so that's what climate. Weather is what's happening out there today. Okay, it's raining, it's cool, the wind's blowing. That is weather. Climate, composite, large weather patterns occurring over numbers of years, which could go up as long as millennia or longer. Okay, if you're talking about glacial stuff like oh goodness, I can't think of the name of it. There was a movie by this name, Ice Age. Okay, the ice ages are tens of thousands of years apart. Okay, so it's pretty major. Okay, I think that was another chat. We have, I think we're up to 10 students now, so let me make sure that's what I've got in the book. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got it. Okay, so that's what climate is. Composite, large weather patterns occurring over numbers of years. Centuries, decades, centuries, millennia, and longer. Now, climate is the determining factor in a bunch of stuff. For instance, the types of plants and animals at a given location. For instance, do any of you have orange or lemon trees in your yard? Grapefruit trees? No, they don't grow at this far north. Okay, they just can't. They cannot survive the winters we have here. Okay, down in South Florida, I doubt if you're going to have many pecan trees. Now maybe you do, I'm just making something up, but pecan trees, you know, those things grow in a certain area. When I was in Nebraska, I only knew of one family that had a producing pecan tree in their yard. The other pecan trees either didn't produce or were too lousy or something. I only knew of one family. Somehow that one adapted and produced pecans at least every now and then. Okay, animals, same type deal. You don't see kangaroos where we live. Well, that's mostly because Australia is an island continent, so they don't move. But certain animals just don't exist in certain areas. Period. We don't see any grizzly bears in Alabama. Black bears, yes. Brown bears, maybe. Grizzly bears, no. Okay? So, yeah, different types of plants and animals are in given locations. And that's because they're adapted to the climate in that region. So the climate is the determining factor there. It's not how far north or south it is, except in terms of climate. Now, also the types of houses built. I worked, I think, about 8 years in radon research, and we worked with a group that came out of upstate New York, and they were just amazed with the fact that down here we didn't have nearly as many basements as they have there, and what's more, that the foundation walls of a house didn't go feet into the ground. they were sometimes just inches into the ground. And they called it the frost wall, okay? Because they had to build their walls down that far in order, and so when they went several feet down, why not build a basement here if you have to dig that far to get your foundation walls? They had to keep the freeze line outside the house because they didn't want pipes and things like that freezing under the house, okay? So types of houses built. But not only that, I don't know if y'all are more familiar with the Birmingham or the Bessemer campus, but I know on the Bessemer campus there's only one building that I can think of on the Bessemer campus that doesn't have a flat roof. Okay, there's one building, they rehabbed it, and it has a slanted roof. Now on the Birmingham campus, I think I'm not sure, but I think the ACAP building may have a slanted roof, but even that new Academic Success Center, I think they built with a flat roof again. I know all the classroom buildings were flat roofed. Okay, guess what? Up in Minnesota, they don't have that. Why? They have so much snow in the wintertime that would collapse the roof. You can't have a flat roof in areas that are going to have a lot of snow. Not going to happen. In fact, in the Alps and places like that, you have enormous amounts of snowfall. Notice how those alpine lodges are. A-frames, really steep A-frames, so the snow will make sure that the snow slides off and doesn't build up. Even the roofs that we have here, I look at our garage, our building out there, they're sort of like this. They're slanted, so rain goes off and that kind of stuff. And if we had much snow, it's going to accumulate because that's not steep enough. When you go like this, yeah, the snow will slide off too. So the types of houses built. Unfortunately, we don't do nearly as much insulation down here as they do up north because they're trying to keep their houses warm. We need to do just as much insulation here because we need to keep our buildings cool in the summertime. Okay? Lifestyles. Yeah, big deal here. Have you ever noticed where the schools that have the strongest swim teams are? Mostly in the South. California, Auburn has a great swim program. I'm sure Florida does. Why? People can swim year round there. Guess what? Up in Canada, they're not really known for their really strong swim teams. However, they play hockey, don't they? We lost somebody, I think, because we're down to 9 students now, but no new ones are coming in. Okay? So, your lifestyle. We do lots of hiking here because all year long you can go out and enjoy. And up north, they may do cross-country skiing. That's a very different lifestyle from hiking, okay? Everything will be different. So sure, climate is a determining factor in plant and animal life, architecture, lifestyles, all sorts of things. Climate also influences or is influenced by, I don't know what, it influences the shape of a landscape, okay? We've mentioned several times before, our soils down here tend to be very thin, okay, and pretty poor because we have chemical weathering going on year round, basically. Only a few days at a time or weeks at a time in the wintertime does it really get cold enough that the chemical weathering almost grinds to a halt. Whereas further up north, months at a time, you will not have chemical weathering. So their soils tend to keep their nutritional value and stuff like that. So that goes right into types of soils. We have a lot of rainfall, we have a lot of erosion, especially when the shape of the landscape's involved. Guess what? Out west where you don't have much much rain, in the desert areas, it's only the wind going to blow those soils away, and hopefully you don't have too much of that. And of course, those both influence agricultural type and productivity. Those deep, rich topsoils they have in the Midwest, Nebraska, Iowa, Illinois, Indiana, Kansas, those things, all that good old topsoil that the glaciers brought down from Canada, thank you very much, and then retreated. They left them when they melted and went back. They can grow I mean, corn and soybeans like you wouldn't believe. Okay? They can't grow peanuts though. Peanuts require a longer growing season. Peanuts require a different type of soil. Peanut production is here in the southeast. Okay? Um, they can they can put their rows really narrow. They can put the plants really close together and still produce tremendous crops. Okay? Down here, you have wider rows, not as dense a plant population, just because our soils are so poor. You have to put so much fertilizer on, it would not be cost effective. Up there, yeah, they put some fertilizer, but they really don't need that much. Okay, then you go further west where it's so much drier, totally different agricultural type there and productivity than what we have here. Unless, of course, you irrigate, and that's what they do a lot out west. The problem with that is irrigation waters sometimes will contain minerals that will not be in rainwater because they are things that have washed off the ground and stuff like that. And you have all sorts of problems with wildfires and so yeah, climate influences just about everything. Okay? I guess if I stay on the slide too long, it won't move. So let's look at the major climate groups. Okay? Two primary factors here that determine these. Number one, I would say the intensity of the incoming solar radiation. Okay? And what does that depend on? Where you are on the globe. If you're on that part of the globe that is right near the equator, plus or minus 10, 15, 23 degrees, something like that, you're going to have fairly intense solar radiation most of the year. Now, the intensity of solar radiation determined on the angle of incidence. If you're right there on the equator, then the radiation comes straight through. There's only that much atmosphere it comes through, and it comes straight to the and hits you in the planet there. No problem. But if you're on the part that curves up and the solar radiation coming in, think about that. It's going through more atmosphere because it's coming in at an angle. So it's losing intensity as it comes in, and then it comes in and bounces off because it's oblique. It's not perpendicular. Okay? So determined by the angle of incidence. Up near the poles, phew, it just is scooting by, skimming across. You get very little direct radiation from the sun. And sometimes of the year, you get none. Okay, period. Now, that goes into this second factor, the number of daylight hours. What happened on Tuesday? Do you remember? What was Tuesday? I asked this question on Tuesday and someone got it right. Autumnal equinox. On Tuesday, we had approximately everywhere on the planet the same number, just about everywhere, 12 hours of daylight, 12 hours of darkness. And guess what? Today, just a few minutes more darkness, a few minutes less daylight. Okay? And that trend's going to continue up until December the 21st or sometime around there when we reach the winter solstice. Okay? The number of daylight hours are going to be reducing every day. Not by much, just by a little bit, but they will be reducing every day. What does that mean? That means the sun is up there less, so that it is not warming the air. Whoops, my internet connection is unstable, so I'm going to quit talking about climate. Okay, and now I'm going to get back to climate. Did I break up some there? Well, not getting a response, so hopefully it wasn't too bad. Just a little. Okay. Um, so the number of daylight hours, that determines how much heating you get from the sun. The longer it is without sun, the more it cools off. And already, I mean, this week has been the coolest week since some. What's that? Did you say something to me? Okay. I can't hear you now.
Yeah,
Uh,
you were breaking up.
I was breaking up. Sorry about that. I didn't have an indicator on my screen saying I was. Okay, so the number of daylight hours determines how long the air, the atmosphere has to warm up. Okay, now having to do with that number of daylight hours, that has a lot to do with the tilt of the Earth, the tilt of the Earth's rotation axis. Because we are tilted, that means from now on, we're going, okay, right now we're just about tilted with the sun being here, we're like this, so everybody's got about the same number of days. But as we move along like this, then the tilt of the sun is going to have less and less sunlight hours until December 21st or somewhere around there. And then it's going to be getting, in general, cooler all that time. Okay. So, what's the outcome of all this? The equatorial regions near the equator receive more solar radiation. Period. Summertime, wintertime, it doesn't matter. More solar radiation year round. The intensity changes on a yearly basis. Now, this doesn't seem to fit here very well. Not equatorial regions. This is in general. Intensity changes on a yearly basis. In other words, especially where we live, it's more intense in the summer, less intense in the winter, of course. And the same thing's true in the south, it's just they have different summer and winter. The number of daylight hours varies annually. Now, I think I've told this before, but I'll say it again. Several years ago, I had a student in the class, this class from pretty close to Nairobi, Kenya, I believe it was. Nairobi, Kenya is very close to the equator. I can't remember if any of you picked that as one of your cities in Africa when you did latitude and longitude, but if you did, you knew it was just a few degrees north or south of the equator. That's all, folks. And she said one of the hardest things she had to get used to, I would have thought it was having seasons. Uh, Summertime really hot, wintertime really cold. I figured she had never had that kind of cold before. And yeah, I think that did have an influence. But what she said in class, the hardest thing she had to get used to was the fact that the number of daylight hours changed. Because everywhere near the equator, you have almost always 12 and 12. A few minutes longer or shorter, but it's almost always 12 and 12. Whereas where we live, we did the calculations. It's more in the biggest variations are something like 10 and 14 in winter and summer in near the solstices, uh, 14 daylight and 10 darkness in the summertime and 14 darkness and 10. She wasn't used to that. She found it unbelievable that places would have different lengths of daylight hours because she had lived her whole life near the equator. Never had thought about that. So, number of daylight hours varies annually. That's everywhere except the equatorial regions. So that's why these two things really don't fit there. They deserve their own bullet. Okay, so let's move on to climate and latitude. Now this is basically going to be pretty much page 589. Uh, very bottom part, well, the left-hand column and moving there. And if you've got the little book, that's 23-17. Now the low latitudes, and when they say low, that means small numbers, 0 to 15, 0 to 23, north or south. Low latitudes, high solar radiation, which we talked about several times already. The yearly variation is very small. It's basically pretty hot all year long. Okay? The temperatures are uniformly high, like I just said. They don't ever drop to really cold. Okay? I think I had a friend whose sister lived in Hawaii for a while. Her husband was in the military. I had a nephew who was in Hawaii for a while. And basically, the difference between their summer and winter, maybe their nights went from the or days went from the upper 80s to the upper 70s or something like that. I mean, it was very little change, maybe 90s to 70s, but it was very little change. Now, the middle latitudes, that's where we live. Here we have higher solar radiation in one part of the year when we're facing to the sun, and we have less solar radiation when we're facing away from the sun. Right now, we're just about equal solar radiation, because we're spinning right around almost 12 and 12. Okay? Overall, the temperatures are lower than they are in the low latitudes, but with much greater variation than the low latitudes. In other words, our summers could be quite a bit hotter than it is right on the equator. Now, some places on the equator could be quite hot, but because we're pointed toward the sun, then we may be right. But boy, our winters are way, way colder than anywhere they're going to have in the low latitudes. So therefore, we have greater variation than in the low latitudes. Now to the high latitudes, that's up near the polar regions. The amount of radiation during one part of the year is very little, and this is showing this. Low latitudes down here, and they show up from the Tropic of Capricorn, 23.5 degrees south. Remember that 23.5? That's the angle of the tilt of the sun, of our axis, okay? The sun doesn't tilt, we tilt. Up to 23.5 degrees north, the Tropic of Cancer. The sun is always directly overhead somewhere in that low latitude. Never directly overhead where we live or down here, okay? Only sometimes during the year it's directly overhead, usually twice in these areas here, okay? Let's move to the high latitudes. The high latitudes is 66.5 degrees north. Now, where did that come from? Well, take 90 and subtract 23.5 from it. That gives you 66.5. Add them together and see if you don't get that. 5 and 5 are 10, carry 1. 9 and 3 are 6 and 3 are 9, carry 1, 10. 6 and 2 is 8. Carry 1, 9, 90 degrees. So therefore, 23.5 degrees from 90 is going to give you your Arctic Circle, and down south it'll be the Antarctic Circle. Okay? So that's your high latitudes up here, your low latitudes in here. Anything in between 23.5 degrees and 66.5 degrees is approximately called the middle latitudes. Now notice, direct sunlight just about anywhere in the low latitudes are awfully close to direct sunlight. Here, notice the angle is greater, okay? Meaning a little more sunlight is deflected off the earth back into the atmosphere. Up here, the angle is really, really great. So this comes along, skims along, and scoots right off there. More of it gets reflected than is absorbed. So that keeps it colder, much colder. Okay? Now, if you look at this, we are so lucky. The vast majority of the U.S. is in this very warm temperate area. Perfect conditions. Yeah, it gets cold up in Minnesota and New England and some places like that, but not nearly as cold as Canada or Alaska or places like this. Really hot in much of Mexico, Central America, and North and South America. When you get down here, there's just a lot less of South America there that's in that nice temperate area. So we are so fortunate, okay? So we're right there in the middle. All right. Any questions on this before I leave it? All right. That then leads to the talking about climate zones. And this is in the right-hand column of page 589 or 23-17. The climate zones are defined in terms of yearly temperature averages. Okay, not maxes or mins, averages. The tropical climate zone, of course, are those near the equator. And again, like we said on several other slides, they receive most of the direct solar radiation and therefore they're hot. The average yearly temperature is hot. Now, like I said, our summers may be as hot as their summers, but see, they don't have any cold winters, so on average, my internet connection is unstable, so I'll quit talking about climate zones. Okay, did I break up some then? Okay, am I better now? Okay, so my internet went weak. I don't think it's mine, I think it's the internet in general because I don't think my bars decrease that much. Okay, so let's jump to the polar climate zone. Least amount of solar radiation, winter or summer. Okay, even when they're pointing toward the sun, it's at a very oblique angle and not much of it gets through. So sure, they may have 24 hours of daylight, but the sun's never directly overhead. It's always down near the horizon. In the furthest north it gets, maybe 20 or 30 degrees. Well, I guess it gets 40 degrees maybe north, but not much. Nowhere close to 90 and nowhere close to overhead. So even in the summer when they have 24 hours of daylight, it's not that warm, okay? It's cold. The constant daylight during part of the summer, constant darkness during part of the winter. You talk about cold, it really gets cold then because no sunlight comes in even to warm it up a little bit. We're right here in the middle. Temperate climate zone, intermediate between the other two, intermediate amount of solar radiation, intermediate in the degree of differences that you have there in amount of variation, everything sort of intermediate. Now, why this statement is on here seems like it has nothing to do with what we're talking about. Rainfall patterns shift seasonally. Okay, we weren't talking about rainfall, we're talking about temperature, but it's true. It's an absolutely true statement. In fact, remember that student I talked about from Kenya? I'm pretty sure Kenya, like a lot of the rest of the world, especially the equatorial world, they don't measure their years in summer, fall, winter, and spring, or maybe they do, but they're just sort of titles. What they talk about are rainy seasons and dry seasons. And I think that's sort of what. Okay, yeah, you're from Uganda, right, Matthew? Yeah, that's what I thought. And so, yeah, your temperatures don't vary that much, do they? Nope. And your daylight hours and darkness hours don't change much, do they? Yeah, it's 12 and 12 just about every day. However, you have dry seasons and you have wet seasons. So that's what they kind of slid that in here for you. That's part of climate for sure, but we weren't talking about that then, but that's what they do. Now, what I don't understand is why we don't have that kind of pattern. So much of the rest of the world does have monsoon seasons and dry seasons. That's that's what they've got. Even Hawaii does have that to some extent, but we don't. We have, yeah, our rainfall varies. In fact, we're coming up, believe it or not, on some of the driest times of our year. October is traditionally the driest month of the year. Now, we're not there yet, but we don't notice that. We don't notice droughts then. Why? Not as much solar radiation. So therefore, not as much is evaporating away. We don't notice. The plants are sort of scaling back for the winter time. Yeah, they don't really care that they're not getting as much water. Okay? Now, when we have a dry spring, that can have terrible consequences on our agriculture. Okay? And when we have intensely dry summers, that also can be, but usually in the winter time, yeah, the rainfall can can vary and go light, and we don't really notice that much. Or it can be heavy, and we just hope we absorb as much as we need. But who cares? It's winter, nothing's growing anyway. So that's definitely true. Rainfall patterns do shift seasonally and major seasonally in much of the world. Not so much here. All right. Now here are the climate zones, and if it looks, I just want to do a contrast here. Remember that last globe? It looked like everything was nice level lines. That's just how we define the low latitudes and the middle latitudes, by those 23.5 degree. Uh-oh, my internet connection is unstable, so let me quit talking about climate. Okay, did I break up some? Well, don't know. Just a little. Well, guess what? Here, everything doesn't go by the Tropic of Capricorn, Tropic of Cancer, and the Arctic Circle, Antarctic Circle. You can be really cold here. You can be moderately cool here sometimes, or warm here. So yeah, it doesn't. This is more realistic. There aren't that many straight given boundaries. They sort of wave a little bit. The tropical climate zone is approximately inside the tropics. There's 23.5 degrees. See, some of this is temperate the way it looks here, and some of this is tropical the way it looks there. Here's tropical, where it's above that, and here it goes back below it again. Here, this is surprising. That would be, no, that's not. That makes sense. Down here, there's even more variation. Well above here and well below here. Way above here and way above here. And that's largely due to the landmass effect and stuff like this, okay? And the polar, look how far the polar reaches here. There's a Antarctic Circle down there, and just about, it's totally within polar, and even up into the tip of South America, which is called Cape Horn, I believe it is. That is some of the roughest, meanest, nastiest weather you'll ever run into or want to run into. And the reason is it's got polar influences and temperate influences, and as two major oceans come together there, it's a mess. And they say this is really treacherous sailing there. That's why the Panama Canal was such a boon. Then Europe could trade with the west coast of the U.S., Asia could trade with East Coast and Europe. I mean, it just made for everything being so much better. Ships didn't have to go all the way around South America to get even from the west coast to the east coast and back and forth. Now, shipping, you can just go through the Panama Canal and you got it done. Now, that was before railroads were really big and interstates were really big, but that was our major form of massive transportation. So this is more realistic. These zones are not fixed lines. In fact, these wavy lines are they're way too smooth to represent all the variations you could have. Okay, so that's about, but it does follow the general pattern. Up here, some parts are temperate inside the Arctic Circle. Here, no temperate regions are inside the Antarctic Circle. So there is some variation. Here, quite a bit of northern Alaska and Canada, even though it could be below the Arctic Circle, is still polar because it's really, really cold. Okay. Now this one is one of the worst slides in my mind. Here we're talking about regional climate influence, or these are, climate zones again. Still talking about climate zones. That's sort of what we were talking about before. But this is a terrible slide. See, this rainfall pattern shift seasonally, that belonged with this slide here because this is rainfall patterns. And I'll guarantee you that there are not sharp, straight angles and corners there. This needs to be drawn more like this. Smooth, irregular curves. There's no solid lines like this. This is probably not bad. Very wet in the equatorial regions. Here it shows the southern equatorial. This is the northern equatorial. Mostly because of South America here. If you went to Africa, that would be a little different. Asia would be a little different. And this is a bit bizarre too. Dry in here, poor old Mexico. they, they just can't catch a break there. Much of Central America, though some of Central America is wetter than others. Like the Yucatan Peninsula of Mexico is a bit more tropical in the moisture sense than the rest of Mexico is. And Costa Rica is not quite as dry as Mexico and stuff like that. Cuba, just off southern Florida, they have they have monsoon type weather there. And why Florida doesn't or doesn't to the degree, I don't know. But look at good old lucky US. We're wet here. Just about the entire country is wet. Now, sure, that's not true here. There are places, these are climate zones, big, again, large scale, small scale. This is large scale. Pacific, the Southwest, very, very dry. So there should be a spot of dry right in here. But this is just a general thing. Most of the U.S. has decent rainfall, except for a few areas. Okay? Hawaii would be somewhere right back in here. And this is probably why they have seasonal. Probably different seasons of the year. They're in the wet range and other times they're in the dry. They're not moving, but these boundaries change. But I guarantee you there's no sharp 90-degree angle like you see here. That's basically landmass. See, there's land over here, water here, here, and that's the major reason they have. But again, these lines would be curved and blurred somewhat. Okay? So, but the Andes Mountains will cause some major changes. And that's probably what this should be. It should be following the Andes Mountain range here. Okay. Oh yeah. So this slide is still doing here. It was for this one because this is the rainfall amounts. And again, that's idealistic. It's not realistic. Okay. Now we turn to, and this is not following the book quite as well as it should, what we're calling describing climates in the book. That's what the slideshow is calling regional climate influences. And here are the four major factors. One is altitude. What is the overall gradient of the landmass? Is it well up here? Think Nepal, Tibet, those kind of areas. They're way, the whole area, even flat areas, way, way above sea level. Okay? Higher altitude air radiates more energy back into space. And that kind of makes sense. Oh, my internet connection is unstable. I'm going to quit talking about even before I said the internet cable. Is that right? Okay, sorry. Okay, sorry about that. It's probably lagging what's really happening. Altitude, if you think about the further you are up into the atmosphere, the less atmosphere you have above you. Okay? The less atmosphere above you, the atmosphere acts like a blanket, keeping us pretty stable. Since there's less atmosphere above at high elevations, more radiation gets bounced back into space because radiation coming through the atmosphere tends to lose energy and become infrared radiation, which is heat. But if it gets deflected off before it becomes heat, then you're colder up there. So that's why mountaintops, like you've seen, they can be snow covered, whereas down at the base of the mountain, you may be in shorts. Okay, you're not going to be in shorts up on top of the mountain. It's a major change. So altitude, higher altitude air radiates more energy back into space. Now, how is that different from mountains? It seems like these are the same, except this could be, as I started off saying, the whole country is at a high altitude. Not just the mountains, you know they are, but say Tibet and Nepal. The whole entire nation is at high altitude. Okay, something just popped up here, but I don't think anybody else came into the class. Okay. Um, Now, cooler air at higher altitudes, almost saying the same thing here. Now, here's another, and this is a very good statement, and yet other places you'll see it not quite stated this well. And here's what we mean. Let's picture the Pacific Ocean, that huge ocean to our west. Most of our winds are coming west to east. So in the Pacific, the winds are coming off that huge ocean there, hitting the continental U.S. here. Not just the U.S., all North and South America, hitting that. When they do, the first thing they hit, and let's go back here to a globe that shows it, and I'll try to point it out to you. It won't go back. Let me get it to go back. Okay, this is a pretty good one. Okay, all along the western, wait a minute, Amari is coming in, or at least his phone is. So let me get Amari here. All right, Amari's here. So we're up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 students here. Let's see if that's what we got. Yep. So I think I got everybody. Yep. Now, we're in chapter 23, weather and climate. We're in the climate part now. We're right along page 592 or so. Okay. This slide is from the previous page, but I went back to this slide. Along the western strip of North and South America, we have the Rocky Mountains, the Sierra Nevada Mountains. I don't know what their names are down here, but there's mountains all along here. There's some mountains in Central America. When you get into South America, we have the Andes, which are really, really tall mountains, and they just hug the coast here. Well, that's because of plate tectonics. The Pacific plate is subducting under the continental plates there, and you get this bending, folding, faulting, and volcanic activity, all forming the mountains there. Well, guess what? The air that's usually coming, especially in the temperate region, west to east, when it hits the mountains, it goes up the mountains and starts losing moisture as it goes up. That's why Mount Rainier always has snow on it. Most of those mountains usually will have snow on them, especially on the west side, because all that moisture drops out. Then on the east side of the mountains, it's drier. Now, I hate to say east and west, and here's why. This is the better statement here. The upwind slopes are wetter, the downwind slopes are drier. That's what's making the difference. Which way is the wind coming from when it hits the mountains? In the equatorial regions, if there were mountains here, winds that hit the mountain on the upwind side would be wetter, downwind side would be drier. Now, that doesn't happen much in this side of Central or South America or North America, but if you go out west to Japan and some of the places there, you do have mountains on the east side of the continents, and then you do that greatly influences the weather on the other side. So this statement here is the best one. Wait, where was it? Yes, upwind slopes receive more precipitation, downwind slopes receive less, because the upwind slopes, you're cooling as you go up, and therefore you're dropping out the moisture as you go up, and then when you come down the downwind side, you're warming up, and what little moisture you have left over gets retained in the air. It doesn't precipitate. And that's why, let's go back here again, in Southern California, say, they can get reasonable amounts of rainfall, but go inside the mountains dry as a bone. When I lived in the San Francisco Bay Area, I was on the ship then, and we were inside the mountains. We had to go through the mountains to get there, driving. You went through big tunnels to get from San Francisco to Concord, which is near where the ship was housed. You went through a mountain. On this side, it would be green. On this side, it would be brown. It was just amazing. You went through those tunnels, and on the downwind side, it was brown, dry. On the upwind side, green and lush. And you drive through the mountain. You wouldn't go through it more than, probably half or three-quarter of a mile, but your environment was very different on either side of the mountain, year round, just about. Okay? So the upwind slopes receive more precipitation, the downwind slopes less. Now, other regional climatic influencers, large bodies of water. And here's why those are so important. Water has a very high specific heat. Okay, what does that mean? It takes more energy to heat water, 1 gram of water, 1 degree Celsius, or let's just call it Celsius, than it does metal, air, um, just about anything. Water has one of the, if not the highest, I think helium has a higher specific heat, but there's just not that much helium around. Just about the highest specific heat of any material on the planet. Okay? So therefore, it takes a lot of energy to warm up water. So therefore, if you're down, and this is true, my wife's family used to usually take vacations, about a pretty major vacation, about once every 2, 3, 4 years, something like that. They planned these trips way in ahead, looking forward to them. And a lot of times it was going to the beach, because that's what they had always done, is go to the beach in the summertime, which was okay. I'm just not much of a beach person. Okay, I don't like being out in the sun unless I'm doing something that I need to be out in the sun, but just lying around is not my cup of tea. Just to get hot and sunburn, that's not where I need to be. But anyway, they did that. And as you drove south in the middle of summer, it just kept getting hotter and hotter and hotter. It seemed like Montgomery was always a degree or two hotter than Birmingham was, maybe more. You keep on going south, it got hotter and hotter until you got near the Gulf of Mexico, and suddenly the temperature dropped, and you started getting those winds coming off the water. Why? Because the soil has very low specific heat, water very high specific heat. It doesn't take that much radiation to warm up the soil several degrees of temperature, where it took a lot more heat to warm up the water. So therefore, the wind coming off the water, even though it was coming from the south, it always seemed cooler, much more pleasant there right on the Gulf than it was just a few miles inland. Okay? So large bodies of water can have that influence. And I think I mentioned last time Lake Erie. Buffalo, New York, Rochester, New York, those kind of areas. Let's see if you can see it. There are the Great Lakes right there. This I think is Superior. That is Michigan. Lake Ontario, or Huron is somewhere in there, Ontario, and this is Lake Erie. And right on the edge of this, the eastern edge of Lake Erie, I think is where Buffalo and Rochester, New York are right in there, and that influences their climate way more than, say, down here. You don't have a large body of water. They get lake effect snow in the wintertime, with other parts of New York. Okay, here comes the internet connection being unstable. Let me stop talking about climate. Okay, I'm back again. So anyway, large bodies of water do have a large influence. Now, large body of water, how about oceans? Is that big enough? Well, not just the large body of water, but the currents. And this is what I was talking about before. That can bring water nearby that has a very different temperature from land. We're going to talk about this in a lot more detail in chapter 24, but this is a foreshadowing of it. Here are some of those. Here is the North Equatorial Current. This is all within the tropics here, keeping everything warm, but of course it's in the tropics. It gets up in here in the Gulf of Mexico. Even though we're above the tropics, it keeps us as warm as tropical water. And that's why hurricanes can form, and we've had several this year, form in the Gulf of Mexico, because we are that warm. The Gulf of Mexico is. But not only that, it goes up from there, and that's called the jet stream. And look at this. The entire eastern seaboard, pretty much of the U.S., is affected mostly by the Gulf Stream, bringing this warmer temperature water here than what the land will ever be in general. Okay, winter, summer, whenever. The water tends to be warmer, especially in the wintertime when the land is cold enough it's freezing, but the water is warm enough to keep it from freezing. And that's why every one of our eastern ports are frost-free, freeze-free. However, poor old Canada up north of us, they get this Labrador current, which comes from the Arctic region, bringing colder water down than what you would find on land, and many of their ports are frozen solid in the wintertime, where most of ours are ice-free. Okay? Now, on the west coast, things are a little different. We have these currents. The North Pacific current tends to be a little warm. It's way above tropical, but it tends to be warm. It turns around and keeps the Canadian ports pretty warm and the Alaskan ports pretty warm. I don't want to say totally ice-free, but much warmer than they ought to be that far north. But this California current that comes in and splits down, now this very temperate water here, which is warm, is moving down into closer to being subtropical temperatures here, and yet the water is so much cooler than the land is because of that current is coming from further north heading south. And that makes, for instance, San Diego, California, which is way down here, just about as far as you can get south in California without going into Mexico. Tijuana, Mexico is right across the border. If you go to the beaches out there, number one, they don't have very wide beaches because the land goes straight down into the water. But what beaches you do have, most of the people wear wetsuits in the summertime because that water is chilly. Now, it keeps San Diego at a very pleasant temperature year round, okay? But you just don't go out into the... Whereas here on the East Coast, that Gulf Stream, if you go to the beaches in New Jersey, Long Island, any of those type areas, in the summertime, everybody's in shorts and swimsuits and stuff like that. It's warm there, and that's way further north than San Diego is, and they're in wetsuits there at the same time of year. So these currents, these are some of the things we don't understand. Here is that one coming up from bringing cool water up the coast of South America into, and I mean, this is a tropical region here. I mean, there's the equator right there. And yet this is cool water coming up here, and that influences things. El Nino is somewhere out here. The place in the Pacific Ocean which causes El Nino and La Nina is somewhere out here. It is very different from what we'd expect. And it influences temperatures in the west, it influences temperature in the middle of the U.S., and it influences temperatures where we are too. And we don't know why. We know they happen, and we can predict them somewhat, but we still don't understand the why. Okay, so ocean currents can be great influencers of regional climate conditions. Okay, now, here's a problem. This is the one I've been talking about all along. There aren't any sharp boundaries. Those things went like this and like this. No, that doesn't happen. Uh-oh. Internet connection's unstable. I'm going to quit talking about climate for a while. Okay, I'm back. Okay. The problems are there aren't any sharp boundaries. You can't say, oh, here it's tropical, there it's temperate. No, it's always a moving border. Okay, a moving boundary line. Okay. No two places have exactly the same climate. We talk about them as if they did, but in reality, they don't. Okay? For instance, out in California, just north of San Francisco, that's where a lot of the great California wines are grown. They have a wonderful place for growing grapes. They call that Mediterranean climate. And in many ways, it's a lot like the Mediterranean climate, where in Italy and France and those places, they have great places for growing grapes and making fantastic wines. Our California wines will challenge them any day, okay? However, they're still not the same. There are very different differences, very big differences between the climates, even though they're very similar. Okay, no two places have exactly the same climate. Okay, now what's going to follow next, I think, is one of the most interesting part of this discussion. Now, the big scale stuff we've been talking about is very interesting, but this next part is going to be talking about North American climate zones. So we're getting fairly close to home, okay? Regional climates, not worldwide, regional. And here's what we hit. Major climate zones in the U.S., we have several. We have marine climates. Now, if you remember from earlier in the chapter, you have tropical marine uh, and polar marine, okay? We're not really going to distinguish that much. We're just talking about whether they're near the ocean, that will be marine, and here they're influenced by air masses coming from the ocean. Whether they're tropical air masses or uh, polar air masses. Okay, we'll get to this figure, and this is a very interesting map to me. Maybe it won't be for you, but I found it very instructive. Okay, then we have the continental climate, far from the ocean, influenced mostly by air masses coming from large land areas. Coming from Canada, those could be polar air masses. Coming from Mexico, those would be tropical air masses. Okay, now that's big, large scale things. Excuse me, my throat is going dry on me again. Okay, now there are other classifications that are intergrades. Arid means very dry. Semi-arid means not quite as dry. Humid means pretty wet. Okay, and you'll see several of these other classifications. Okay, here's the big map. In your book, you can see it better. Okay, actually, table 23.1 lists and defines some of the descriptions probably better than this very short few words that they do on the map. So kind of look at it, table 23.1 on page 592, while you're looking at the big map on 593. This is a rendition of it, but the map in the book is easier to read in my mind. So I'm going to scoot my computer over a little so I can scoot my book over a little and see the map a little bit easier. Okay, let's start up north, cold. This white part up here, polar. And you can, okay, remember the Arctic Circle was 66.5 degrees. So that was somewhere right up about here, a little above there, somewhere maybe right in there. That's 60, 70, 66.5 would be somewhere here. So some of this polar is below the Arctic Circle. Some of it is right on the Arctic Circle or just slightly below. Okay? It depends. But like they said, no sharp boundaries. Okay? The closer you are to water, the more likely you'll be influenced by that water. Okay, so this white area here, they just label it as polar. Okay, very cold, not much you can do with it. It's just cold, really cold. Okay, then they have humid continental, okay, subarctic. That would be this sort of purplish band through here. Much of the state of Alaska, much of the nation of Canada, and certainly over here, Nova Scotia here, I believe that is, and stuff. So yeah, this is humid because it has a fair amount of moisture. Continental because it's mostly influenced by continental air masses. Okay, now a little caveat here. We say it's humid. That doesn't necessarily mean it has that much more rainfall than you have further south when some of this is humid too. It's so cool up here you don't lose the moisture like you do down here. Okay? So it is humid overall because it has higher humidity. Okay? Next is humid continental mid-latitude, and that's this part in here. Okay? Now this, just to get a reference here, this is still part of Canada here. Maine comes into play somewhere in here. The Great Lakes are kind of a boundary, Canada to the north, US to the south. This, I'm pretty sure, I'm getting them crossed up now. Maybe this is Lake Michigan. That's Lake Superior there, because that looks like the biggest. This is Huron, and then somewhere here they run them together. Ontario maybe here, and Erie, they don't even show them. Maybe this is Erie. They sort of run them together. But anyway, that's the boundary. So you see some of this is Canada, some of it is US. This will go down as far into New York, maybe northern Pennsylvania here, but then it goes up. So this is mostly into Canada here. Okay, so that's your humid continental middle latitudes. Going on down, humid continental low latitudes. That's this. There's our breadbasket right there. There's Illinois is right here, Indiana right here, Iowa right here, the Dakotas, the Nebraska, Kansas, getting toward, oops, internet connection is unstable. Let me quit talking about climate until that settles out. Okay. Hopefully I didn't lose much important stuff there. So this is the humid continental low latitudes. Continental, and that is largely surrounded by continental areas, not that much ocean. So humid, because, and I'll tell you on the humid part later. Okay, that's we are so fortunate there again. We'll get to it. Let's move on south from there. Humid subtropical. That's where we live. We're not tropical. Tropical is down here. This is subtropical. Generally very humid. Now, certainly times of year may be drier than others, but very humid. So let's do a quick timeout here. Why is all this part, or at least this part here, of the U.S. humid? In most continents, countries, and things like this, where you have a large mountain range here, moisture doesn't make its way across. You would typically have desert on this side. Okay? Here's why. Our good old Gulf of Mexico. Good old Gulf of Mexico is always warm. It's almost tropical. Remember, the Gulf Stream comes in, keeps it warm year round, and okay, here comes Kendra. She must have had to leave and come back. I already have her marked here, don't I? Yes, I do. Okay, glad she's back. Okay, what the Gulf of Mexico does is pump moisture into the eastern half of the U.S. We should be, if it weren't for Gulf of Mexico, we would be almost desert here, because the mountain ranges, remember, the upwind slopes are more moist, downwind slopes are drier. So we should be dry, except for the Gulf of Mexico. And you can see the line here. It's not a fixed boundary, but that pretty much shows the moisture pattern coming from the Gulf of Mexico. Remember, we have mostly western to eastern winds coming in, and that's what prevents it from getting this area as much, because the wind keeps the moisture to this side. But that's what keeps us warm, it keeps us wet, it keeps us the great place to live. Except for the mosquitoes. Okay, no, okay. They have mosquitoes up here too. Okay. Now, that was humid subtropical. The bright blue down here, that's tropical. Okay. Tropical wet. That's the Yucatan Peninsula, as they call it. And there's, I think, Cozumel and some of the places that people love to go vacation. I've never afforded to go to there, but I've heard people talk about it. So wet, so nice, so lush. Basically wet tropical. Then we get down into tropical with seasonally wet dry, like Matthew was talking about, monsoonal tropical. Okay, that would be these areas, including Cuba, right there, surrounded by water, and yet there's seasons when it's very dry. This is Hispaniola, which is split into Haiti and El Salvador. No, goodness, Santa. El, goodness gracious, why am I going blank on the name? Dominican Republic. That's what I was trying to think of. Uh, part of the island is Haiti, part of it is Dominican Republic. This I'm pretty sure is Puerto Rico here. Either this one or that one. Maybe this is Puerto Rico here. But anyway, that's down here. Notice the very, very tip of South Florida is considered to be tropical with seasonal wet dry. In other words, monsoonal. That's what the green is down here. And then we move into semi-arid. And look at poor old Mexico. They've got a lot more water around them than we do, and yet they turn out being semi-arid. Most of the country except for a little bit. Okay? Here it is. Now this would be, and I can almost guarantee you this isn't quite true, but this is fairly close to the continental divide. No, I'm sorry, it's more this way. Okay, but this is the region that the Gulf moisture just doesn't quite get to as much. It's on the downwind slope of the Rocky Mountains and Sierra Nevadas and stuff like this, so it's semi-arid. Okay, these are your deserts. And this is the most amazing thing to me. This is called the Baja Peninsula. I don't know if you've heard of some of the road races and things they have down there. Baja Peninsula. Look at that. Water to the west, water to the south, water to the east, and yet it's a desert. And you think, how could that possibly be? Well, the only thing I can say, it has to do with the ocean currents. It just doesn't deliver the water to the land. And on this side, right next to water, desert. Stretching down into Mexico, desert. Here's our southwestern U.S., desert. Okay? Much of Arizona, New Mexico, into Utah, some of those areas, very, very dry. Okay? Then we have, and I think that word is marine. Now that's not to be confused with tropical wet. This is nowhere near tropical, but guess where you are here? You're on the upwind side of the mountain range. This is a mountain range. It goes up here, it goes up here, it goes up here, it goes around here. The upwind side, so they are very much influenced by moisture. This is the island of Victoria in Canada. Vancouver is right across from that. This is our Washington State, Oregon, parts of Northern California. That's the San Francisco Bay down here. One of the most beautiful areas I've ever been to is Muir Woods. That's where giant sequoia trees grow, and they're on the upwind side, and it's just, in fact, you drive down into it and you go through clouds, okay, because the moisture is trapped between the ocean and there, and those trees just grow to be enormous in size. Beautiful, beautiful sequoias, okay. And much of this strip here, that's the reason, on the upwind side of the Pacific, and the moisture hits the mountain ranges and comes out and keeps this marine very wet, okay. This was that Mediterranean region. There's San Francisco Bay right there. And north of there, there's the Napa Valley, where they grow a lot of the great grapes. And then the Imperial Valley, the San Joaquin Valley, those kind of places in California. Now, it's sort of Mediterranean, meaning it's seasonally wet, dry, kinda. Not as nearly as wet as you would expect it to be, but they do get some. But to support all the crops, they have to irrigate, and they use waters coming off the mountains here and they use that for irrigation. So that's your Mediterranean. And then this brown is what they call the highlands. These are mountains basically. There's the Sierra Nevadas here, the Presidential Range here, the Rocky Mountains come through here, and somewhere in here is the Continental Divide. Okay, the upwind side of the mountains very wet, the downwind side desert, semi-arid, or more mountains. Okay, here you have more mountains down here, and that's what makes for the seasonal tropical with seasonal wet dry, especially on this side. I don't know why that isn't wetter, but it isn't. Another mountain range down here. Somewhere right in here is where the Panama Canal is. Okay. All right. So those are major climate zones here in the U.S. or North America, not just U.S. Example 23.3 is a very, very interesting example. Okay. The trouble is the temperatures are given in degrees Celsius and the precipitation in millimeters. And I don't read either one of those too well. I do understand temperature fairly well. Precipitation, it sounds like 40 millimeters is a lot. It really isn't. That would be more like 4 inches, and that's the wettest thing shown on here. So, but this gives it by month, and it gives the temperature. Now, anything minus there is below freezing. Anything positive is above freezing. Look at that. The only months that average above freezing are June, July, August, and just barely September. Okay? All the others are below freezing on average, meaning in general they're much. So what would that be? You have to be up there, I would think, and the rainfall, not that much. I would almost say polar, but it could be humid continental. Let's see what they say. Polar. That is a polar climate. That's what I thought it was. Those temperatures are just way too cold, and the moisture just isn't great enough. There, the whole month of April, on average, 0 millimeters. I mean, that's less than a dime's thickness of moisture in the month of March on April on average. No April flowers there, folks. Now the next one, the example 23.4, look at those temperatures. There's not a single month that averages below freezing. In fact, most of them are well above freezing. Even January, February, and December, well above freezing on average. That doesn't mean it doesn't get below freezing, but on average, it's above freezing. And look at those precipitation amounts. That March and April way more than what they were on the previous one. June really high, but that's in the heat, beginning to be the heat of summer, so you probably don't notice it that much. October pretty wet, so it's probably not us, but that would be humid subtropical. So that would be that sort of Kelly green that you saw there in much of the southern U.S. That's where we live. Now, major climate zones. I guess I've been on the slide too long. Let me click on it again. How are we doing on time? Okay. Now we're going to look at local climates. This is on page 594, first column, left column, or if you're in the small books, 23-22. And Diana is here. Let me get her in the class and marked on the roll. We are finally getting up to a good number of students, sort of. We broke double digits, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Even dozen. Let's see if we still got 12 people here. Yep, we do. Good deal. Diana, we're in chapter 23, page. This is weather and climate. We're in the climate part of the chapter, the second half of the chapter, and we're on page 594, just beginning to talk about local climates. Okay? Now, when they say local, they can mean really local. A microclimate is a very small pattern in the climate. You can have local climates that could be a bit broader. like we talked about the southeast. That's a pretty broad regional climate. Microclimate, really small. It can be associated with a large city. Okay? And one of the things, I think we had a topic about this, the heat island or heat dome effect. You'll sometimes hear both of those terms. Now, it used to be, and I'll do it again this term too, but I'm not driving. But it used to be on the second mini term, and I'm going to do it this time too, those of you in the class will not start at 1:15, it starts at 3:15 for the second mini term class. It's Physical Science 112. Starts at 3:15 and goes to 7:45. And it used to be, and this will be the last half of the term, starting in, well, I'm going to stop talking now about climate because our internet connection is unstable. Okay, we're back again. It used to be that I would leave campus, pretty close to 8 o'clock at night, and this was late in the year. October was okay, but then moving into November and December, it can get pretty chilly. I would get in my vehicle, and it had a thermometer, indicating outside temperature, and let's just say it was, pick a day, a pretty cool day, say 40 degrees. And as I would drive north and east, going from Bessemer toward Birmingham, okay, you would think going north it might get a little cooler. And you would think going east it might get a little cooler because the sun has been down longer in the east than it was in the west. Not much, just a little bit. If anything, you would think the temperature would go. And number three, it's later at night. It's been longer since the sun went down. So you would think the temperature would be dropping as I drive north, east, and later in the evening. Okay? Well, what did I see on my thermometer? When I left Bessemer, sure enough, I might drop a degree. Maybe. Okay? As I got past Fairfield and those kind of areas, may have dropped a degree. Okay? But then, as I get closer to Birmingham, I gained that degree back, and then more and more. And usually by the time I got near downtown Birmingham, I was up 2 or 3 degrees warmer than I was in Bessemer. Why? Because Birmingham's a bigger city, more pavement, more buildings, everything that would do. Here's what do it. Buildings and pavement absorb more energy in the daylight, and they emit that solar radiation differently than natural vegetation and landscapes do. So when I got over into my neighborhood, which had more vegetation, a lot more trees — we live in Forest Park, by the way, so it's very many trees — the temperature dropped maybe a degree or two. Okay, but passing through downtown Birmingham, all those buildings, all that pavement, and then just think about this: all those buildings, in whatever time of year it is, if they're heating the buildings, they're heating also the land outside. If they're cooling the buildings in the summertime, what are they doing? They're blowing that heat outside. Okay, so everything tends to make it warmer. You have more cars, you have more industry, you have more of everything that's producing more heat. So that can be a local climate, the heat island or heat dome effect of a city. Okay, but it could be as small — this is really a stretch, but it is — a single tree. I don't know if any of you have done much backwoods hiking, camping, and that kind of stuff, but most people who do a lot of that will begin to recognize that in certain areas things look differently. Here in the southeast, most of the time the north side of the trees that don't get as much direct sun on them will tend to have more moss growing on them. Okay? Possibly lichens too. I don't know as much about that, because in the summertime that direct sunlight is going to dry up the moss so it doesn't grow as well. Okay? And other things like this. So even a single tree can show local microclimate effects, okay? Because you have more moisture on one side, less on the other, more sunlight on one side, less on the other. Yeah, it's pretty amazing. Uh, so, I've been on that slide too long. It won't let me advance. Now we get into 23.4. Okay. Oh, and by the way, right above that, just after local climate, concepts applied, cities change the weather. And it is definitely a nice little blurb to read. You'll get all sorts of really interesting information off of it. I listen to public radio, not a lot, but I used to when I was driving. I don't go anywhere anymore. Um, but I used to listen to it to and from work every day. And when I drove around on the weekend or something, if I could find the public radio station, I was usually on it. Well, Friday afternoon, typically when I was leaving work, going home, because I usually work late evenings on Monday through Thursday, so I get off a little early on Friday. And usually when I was driving home, there was a show on Friday afternoon called Science Friday, one of my favorite shows, okay, radio shows. And I believe it was on that some Friday recently when I was driving. I had to go somewhere, rather unusual, but I did. Oh, I think I had to, I don't remember where I was going. But anyway, it was on, and it was talking, the guy on the show was talking with an urban forester. And I believe it was mostly New York City that he was talking about. They are trying their best to get more trees planted in New York. Sure, they have Central Park right there in the middle of Manhattan, which is a wonderful, beautiful place, but they were trying to get them scattered throughout the city. Now, I think Birmingham and maybe where you live, there are lots of trees. We live in Forest Park. This is a great area because of that, because we got a lot of trees. Trees really do affect the climate. And they said if they can get more trees scattered throughout New York, wherever they can get them, they are going to affect the temperatures. They're going to clean up the air some because trees act as filters for pollutants. They're going to just increase the beauty. There's just every kind of way they're going to make improvements. So that's more of that microclimate thing. So cities can change the weather, but I think also proper use of cities, like planting more trees, can bring it a little bit closer to what it was before the city was there. All right, so let's get into climate change. Now, this author does give it some space here and does talk about it, but a few of the things he says I sort of don't agree with. Now, climate change is a departure from the expected average pattern of climate for a region of time. Now that's a weird phrase there, region of time. Time doesn't have a region. I think they meant to say span of time. Okay. That's sort of a definition. Uh-oh, my internet connection is unstable. I'm going to quit talking about climate change. Okay, now we'll be back to climate change. Okay, so this is a change that's a departure from what you expect. Now here's where the big arguments come, and they're not nearly as big as they make them out to be, but they are arguments. People say, wait a minute, we've had ice ages, we've had this, the weather's always changing, this is just part of a normal pattern. Well, part of it is, okay? Part of it is, for sure. The weather does always change. Climate is always changing. But what's happening now is the rate at which the change is happening, and we're going to see that on some of the graphs we'll see, is way out of the ordinary. So this is a departure. Even from the normally expected changes we would have, this is a departure. Now, I know a lot of the weather people I've talked with, I think including Jerry Tracy and Harmony Mendoza and a few of the others, they sound like they're a little more skeptical than I thought they would be, because they know that big changes occur over time, but we're talking about big changes occurring over small amounts of time. Now, here's part of the big argument. We only have good data. Remember, that's why we talked about weather. Good data basically in the last 100 years or so. Decent data maybe a few hundred years before that, but after you go so far back, there weren't any. I mean, this is way before technology. All we have is what we call anecdotal data, little bits and pieces here and there, and it was usually of unusual events. So you can't really count on it that much. So a lot of the data that we do have from way back in time, I keep pointing to this, this is 1000 AD, okay? We're now in 2020 AD. I was born in 1951 AD. Okay, this is way, way before. The U.S. wasn't even here before 1775, right in here. Okay, the country, I mean, the land was here, but we weren't the United States then. So we have very little data, no data from back here. Okay, so what you use is proxy data. Now, what do we mean by that? Here's an example. Drill cores down into ice in the glaciers. And if they can estimate what age that ice is, when that snow fell, they can measure carbon dioxide, oxygen levels, they see what kind of uh, insects or things were trapped in the ice. They can measure, pollutants, all sorts of things. That's proxy data. No one was there to collect it at the time, but we can get information. But that's pretty spotty, because what if you had a major meltdown sometime there? You lost all that data those years in there. And those were the years when the most changes were happening, so you lost the data there. Okay? You'll never get that back because the ice melted. Okay. You can do sort of the same thing with drilling into soil, into the ocean floor. We talked about that when we were talking about plate tectonics. We can drill into, land-based things and try to get a good idea. Remember the pictures we saw of the great Grand Canyon, okay, or some of those canyons where you saw all those layers and layers and layers. It looked like we just lost somebody, because now we're down to 11 students. Okay, hopefully they'll be back. Where the Colorado River, if it was the Grand Canyon, went cutting through for centuries, for millennia, has been cutting through that, wearing away the soil underneath, and what you get there is layer after layer after layer after layer, older and older and older strata of soil. Study the things that were happening, the insects, the things that were living in those layers. That gives you a really good idea of proxy data used to infer past climatic conditions. If you find lots of insects in an area where it's now very dry and not many bugs live, that used to be a lot more humid. So those kind of things. So here, look at, according to proxy data from here, more recent data from here, Earth has experienced a period of warming and a period of cooling over the past 1,000 years, from year 1,000 to 2,000. Okay? Now, this is just an approximate curve here, proxy data. Here you started picking up little bits. This is about the time when Europeans started sailing more, going outside of Europe. This is the time of discovery and stuff. So people were collecting more data, just fairly light and maybe decent records, but not great records. And then over time, we got better and better at collecting and things. Around this time, almanacs started coming out, people recording things, and then nowadays we have really good. Here's the part that's scary. Okay, the slope here is pretty gradual. the change here is pretty gradual. The slope here is still fairly gradual. And then you have the ups and downs. These ups and downs were probably happening here too. We just don't have the data to support them. This is probably normal. Ups and downs, but the trend is up. And all you see is the trend here. You don't see the individual ups and downs. And this is probably normal. But here is where it starts to be a bit abnormal. Look at the slope of that line. You're going some pretty large, half a degree below normal. This is Celsius, by the way. That would be almost a degree Fahrenheit below normal to a little bit above normal in a very short time period. Now, what was happening here on Earth in that time period? This is the late 1900s, the late 1900s. Industrialization. We started burning fossil fuels as rapidly as we could get our grubby little paws on them. We started automobiles. We started industries. We started coal mines. We started electric power plants. We did everything we could, and that's where, look at this. Now, if you also map this, and there will be a picture coming up later, carbon dioxide levels, they shot up almost this entire period at just that level. Now, my internet connection is unstable. I'm going to quit talking about climate change until it comes back. Okay, it's back. Okay, this is what we're talking about. Yeah, there's been some times when there have been fairly major changes in a short amount of time, but these are usually explainable, like maybe volcanic activity or something after a volcano or something like this. This right here, over that long a period and that much degree change and that steep a slope, that's tough. That's tough to explain away. Okay? Now, I can't get it to advance. Here we go. This is a smaller window. This is a 100-year window. That was a 1,000-year window. So this covers that period we just saw. Now they spread out the horizontal scale, kept the vertical scale the same, so you don't see that steepness here because they spread out the horizontal scale here. But this is still pretty steep to go from here to there. And sure enough, it did go down a little, but then went back up really major here. That's, I don't think, is sustainable. Now, here they go back and talk about the proxy data. Data about the ice ages and the interglacial warming show that periods of warming and cooling occur in and here's my point, very large cycles. Now let's go back to 1,000 years. There was not an ice age in those 1,000 years. Ice ages have been tens of thousands or hundreds of thousands of years apart, not 1,000 years apart. So even this scale is not talking about ice ages. Okay, those are way things. Interglacial warming, yeah, large scales, and because it was so long, it took a long time for those changes to happen, whether they're decreasing or increasing over long periods of time. We're talking about a change, a really steep change over a very short time period here. That's the big difference in my mind. During the past 100 years, the Earth has experienced two warming cycles. There's that one and there's that one. But basically, there's very little difference. You're talking about just 100 years here. This is just a minor little setback here. Now, what happened here? World War II happened here. 1940 to 44. Yeah, I don't know if that had any influence on it. It may or may not have. I think you had some fairly major volcanic activity that could have driven down the temperatures a bit, okay? But once they cleared, things just climbed like crazy. And this is a steep curve here, okay? And the most recent period of warming over the past, okay, let's just talk about it. Now, temperature changes are not uniform. Now they say this, temperature in the southeastern United States have cooled since the early 70s. Hey, I don't know when the slide was done. It hasn't cooled in the last 10 years. So this slide is probably pretty old, and the data for the slide was even before that. It may have cooled since the early 70s up till this slide was done, maybe in the 90s. Since the 90s, the temperatures have shot up, not cooled off. Now here it says sea ice in Antarctica has increased. Maybe in that period, maybe when this was happening here, but since then they are losing sea ice so fast it's scary. I mean, you can look at pictures of it. Great big chunks of sea ice are falling into the ocean very, very regularly down there. It is a scary, scary proposition. This is old data here. Like I said, I don't know when this slide was made, and the data from the slide is even older. So not happening anymore. Greenland is losing ice like crazy. Okay. Remember those continental glaciers we talked about? Antarctica and Greenland, two of the major places for them. The North Pole used to be solid ice. It's liquid there. I mean, the North Pole is not landmass. South Pole is a landmass, Antarctica. North Pole is just sheets of ice. Basically, you can sail right through up. So I'm running, internet connection is unstable again. I'll stop talking about climate change until it comes back. It's come back. Let's see if someone else came back. Nope, got nobody new coming in. All right. Now, what are some causes for this global climate change? Whether it's naturally occurring or not, what are some causes? One, it's a result of a complex interaction of many different factors, not just a single factor. Sometimes we get a little carried away and put too much emphasis on one, but there's several things. Sure, sunspots. When sunspots happen, that means there is some major event going on the surface of the sun. It's either very much colder or very much hotter than the surrounding areas, and usually when you see lots of sunspots, you have lots of solar radiation peaking coming from the sun. And when that happens, things warm up a little bit. Now, the Earth's tilt, orbital shape, and axis wobble. Okay, now wait a minute. The tilt doesn't change much. If you remember back when we talked about that, what was it, 22,000 years for it to make one circle of that tilt? And that's also axis wobble. That tilt, that's, to me, these are talking about the same thing. Okay, now wait. If you're talking about the tilt of the Earth, it changes as you go around the sun. It's still the same tilt. It's just that happens every year. The orbital shape, that's not changing that rapidly. Yeah, we get further from the sun in July and closer to the sun in January. Yeah, but that happens every year. That's not a major change. Okay, the axis wobble, I think it was something on the order of 22,000 years for it to make one cycle there. That's not going to make a huge difference. Okay, so, but those are all, anything that's happening there is influencing other things. Okay, the greenhouse gases, that's the one I was talking about. Now, the major greenhouse gases are water vapor, carbon dioxide, methane, and then they say trace gases. Okay, I'll buy that. I don't know what they mean by trace gases, but there's not many of them, so they're not going to have as big. Now, water vapor, the hotter the Earth gets, the more water vapor it puts into the air. More water vapor it puts in the air, then the more it traps the heat. So that's a pretty bad cycle there. Carbon dioxide, more carbon dioxide in there, the more it traps the heat. Methane, the more methane in the air, the more it traps the heat. Okay, so these are all things that are coming because of, well, you see, carbon dioxide increase, methane increase, that comes with industrialization, drilling for for your fuel sources and things like that, that's going to create more of these things. That makes the temperature go up, which makes more water vapor, which then increases more. Okay, the trace gases I don't think have that big of an effect. Now, oh, here's Drew. Thank goodness Drew made it today. So I'm getting caught on my own cord here. Let me get Drew here. If I can get my pen to work. Okay. Now, I don't know what we're up to in numbers. We're up to 13. Hey, welcome. Glad you made it. We're up to 13 students. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, got everybody here now. That's good. We're in chapter 23, nearing the end of chapter 23. We're in section 23.4, climate change, and we're somewhere along about page, I probably have a, yeah, we're right at the end of page 595, right hand column. If you don't have the book with page numbers on it, it's 23-23, 23rd page in chapter 23. Now, we're down at the bottom of this slide, and this is one that scares me about as much as anything. Hey, Mr. Charles, yes. Real bad, man. What is real bad? Am I breaking up badly? Is that what you're saying? Okay, I heard you say something and now I can't hear you at all.
Mr. Fowler, I think your internet's cutting in and out. Yeah, you're lagging real bad, Mr. Charles.
Okay, I just had a thing. Yeah, I heard you just then, and now my internet just shut off, so you can't hear me. Let me. When you speak, you're sounding like this. So I think everybody's having the same problem. My Zoom just went off and then came back on. It wasn't rapid. It took maybe a minute or two for it to come back. My internet connection is still unstable, so I'm going to hold off for a moment here. Okay, now it's supposed to be a little more stable. Let me go back to where we were. All right, and now I've got to move everything around again. Sorry. This toolbar blocks my receipt of the slide, and y'all are blocking a little bit, so I'm scooting you over too. Okay. I was just going to say, this is one of the things. Can y'all hear me better now? Anybody?
Yes.
Okay, good. It's something to do with the internet. I'm at 5 bars on my internet here, but it's something once it leaves the house. Okay, the internet is unstable. I don't know if that makes any sense, but anyway, this tropical deforestation. This is something that bugs me big time. Now, it'll sound like I'm blaming other people. I'm blaming us as well. Okay. Now, we don't have any forest in tropical areas because we don't have any tropical areas. We're in the temperate region. But in the tropics, what we always have had, where there's high moisture, warm temperatures, you have these really incredibly dense forest, tropical forest. I mean, the trees grow huge. There's all sorts of other plants underneath the trees. There's ferns. There's, everything you could imagine, really dense, plenty of moisture, plenty of high temperature year round. Trees grow like crazy, and all the green stuff grows like crazy. Now, that's how we are naturally. Okay? Now, if you think about the U.S., I'm going to digress a little bit here. When the U.S. was formed, now, of course, before we were the U.S., we were inhabited by the Native Americans. We call them Indians. They had nothing to do with India. The Native Americans were here. They lived basically in harmony with nature. I'm sure they cleared some trees and built some areas, and they did various things that they needed to make their lives a little better and stuff, but they worked within the natural setting pretty well. That was part of their entire approach to life, to do this. When the white settlers came from Europe, we started taking down trees, we started planting cotton and corn and beans or whatever we were going to do. We just acted like we were in charge. And basically, where we live now in Alabama, I bet you was almost solid forest. I think from the East Coast. In fact, I'm going to digress a little for those who just came in. Well, I can't. It's not cooperating. Oh, here it is. That's the map. Yep, there's the map I wanted. I bet you pretty much everything here in this humid region here, well, maybe this part of the humid region here, everything in this part was solid forest. Pennsylvania, North Carolina, everything was one solid forest. And we came in and just started cutting down like crazy, making our roads, making our cities, doing our farmland and stuff like this. Yeah, we needed it to survive, but we were very indiscriminate in doing so. Okay? Now, out here, goodness, I just dropped it again. Drop zoom again. So let me get the slide back. All right. My internet connection's unstable again. Um, there, we should be back a little bit now. Let me see. We may need to just wrap things up today shortly. Uh, let's just get that out of the way. I bet you what I was showing on the map here, this part was just solid forest. Hardwood forest, I bet you it was beautiful beyond belief. Now, huge spans are not. Yeah, in the southeast we plant trees. We plant pines because those are fast growing trees. They're not the native, I mean, they're native, but they're not the dominant trees. Those would be the hardwoods. So we have done a good deal of deforestation. Of course, we planted crops and things, but that doesn't produce again. But what I'm talking about, let me go back another few slides if I can get this to go back. Okay, down here. Here is the equator. I would say everything from basically that you can see here. If it's got lots of rainfall, which a lot of this does, and this, we're talking Brazil is where I'm talking mostly. Now, if you go to another part of the world, Indonesia, places like this, okay? What they're doing now is going in, and a lot of the same reasons or excuses that we did, okay, when we cut down all our trees, what they're doing is cutting down trees so they can grow more soybeans. That's the predominant thing. Possibly corn, but mostly soybeans. Now, why are they doing that? Well, their populations are increasing, so they need, that protein source. But the other thing, okay, is it breaking up again? I know when you spoke just then, you were breaking up, so I couldn't understand what you said. Okay, is it better or worse? Okay, whatever you just said, it was so broken up I couldn't make it out. So it must be the same with me to you. Is that right? Yeah. You see, when you, uh, okay, I can hear you a little better now. Can you hear me better? Yes or no? Okay, good. So what they're doing in these tropical areas, good. What they're doing in these tropical areas is going in and cutting down those huge, thick trees, just really densely populated with trees. Now, let me tell you what that tropical forest does for us. For the entire planet, that takes more carbon dioxide out of the air and puts more oxygen back in the air. That's what trees do. In the tropics, they do it big, big, big time because there's such dense, lush trees down there. We do it some here, of course, but not nearly to the degree it does down there. Well, when they cut down these trees, now you would hope when they go in and cut down the trees, at least they use the wood. There's more wood there than they can possibly use. They can't make enough furniture. They can't. It's just not economically worth it. So you know what they do? They bulldoze them up into great big piles and set them on fire, and they burn them. So all that carbon that had been taken out of the air for hundreds, if not thousands of years, those trees have been accumulating that carbon. Now it's all being released into the air. So there goes our carbon dioxide, shooting up like crazy. Now why are they doing this? So they can grow more soybeans. Because that tropical rainforest, that soil under there has got a, remember back in the soils chapter we talked about humus, decaying plant material? Boy, does it have plenty of humus. So they plant their soybeans, and maybe for 5 years or 7 years or something like that, they get great crops of soybeans. Now why are they using soybeans? Because they're getting the oil out of the soybean. Because the oil they use for fuel, most of their cars run on ethanol, not on gasoline, because they don't have as readily accessible fossil fuels as we do. So their whole economy is built on producing soybeans. So they come in and maybe for 5-7 years, something like that, they get great crops of soybeans, but slowly, the crops go worse and worse. Why? Because those soils use up and chemically lose the humus. It goes back into the atmosphere as carbon dioxide or methane, one or the other, goes back into the atmosphere, and now they're left with these tropical soils, which are some of the poorest soils in the world. Like I said, our soils are highly weathered chemically, so there's not as rich as those in the Northeast, in the Midwest, but down there, they're even poorer than our soils are. So after a while, nothing will grow. Okay, my internet connection's unstable, so I'm going to quit talking about climate change. Okay, am I back? Can you hear me now? Okay, so in a few years, they've used up the soil. It won't grow anything. What's that? Can you hear me? Okay. Well, what they do after a few years, soybeans won't grow there anymore. What have they done? They've taken that good, rich, tropical soil that was there because of the forest there. They removed the forest, the soil deteriorates away, and now nothing will grow there. It will take literally thousands of years for those tropical forests to creep their way back to where those soybeans were growing. They can destroy them in a week. It takes probably hundreds of years for them to grow back. And all the time they're putting more greenhouse gases into the air. Because in addition to carbon dioxide, water vapor is being put back in the air, because when carbon products burn, the other byproduct, carbon dioxide and water. Believe it or not, that's what comes out of the burning of carbohydrates. Okay, now they're doing it in Brazil to grow soybeans. In Indonesia, they're doing palm kernel oil. Now, if any of you have any food supply there on your I have some goldfish. I'm going to eat one right now. I'm going to look at the ingredients in goldfish. Okay? It's written real small. Of course, there's wheat flour, and it's cheddar cheese because they're goldfish. Then it says canola and or sunflower oil. Thank you very much. Okay, this doesn't have any um, palm kernel oil in it. Okay, goldfish is a good product, by the way, because it doesn't. But look at most of your other snacks or any kind of thing, prepared food, and if it has oil, which most things do, the odds are most of them will have palm kernel oil. Why? It's cheap for them to make palm kernel oil in the tropics. Okay? But what they have to do is cut down the rainforest to get the soil to do that. And then the same thing that happened with the soybeans in Brazil will happen in Indonesia. And then it'll take hundreds, if not thousands of years for those tropical forests to grow back. Whether we have the time for that to happen, I don't know. So that tropical deforestation is shooting yourself in the foot several times over. Sure, that's a cheaper, and guess what? That palm kernel oil is not nearly as good for you. Now, no oils are great for you, but canola oil and sunflower oil are the two of the better oils. The palm kernel oil has more things to clog your arteries and that kind of stuff, and we are eating so much more of that kind of mess is why we should be getting better as far as life expectancy. In the US, we're getting worse. One of the few, if not only, industrialized country that's going backward in that. More heart attacks, more strokes, more things like this just because we're eating so badly, because we're eating the cheaper palm kernel oil brought about by tropical deforestation. Okay. Yeah, those people have to make a living. We need to do a better job of doing stuff. Now, I think y'all have crept back over last time my internet went out, so let's go on. So, global warming. Now, frankly, I find this author not to be the best on addressing this, especially back at the time these slides were written. He may be better now. But the Intergovernmental Panel on Climate Change, that's called the IPCC, was established by the United Nations in 1988. People had been warning about this. Scientists had been studying it for decades and noticing the trends. So finally the United Nations established this in 1988, and they've been collecting data since then. Now here's one of the statements that really gripes me about this author. Despite research, data, and models, the predictions of experts vary. Now, number one, that's old data. Okay? Based on limited data, and the models were not that good back when this slide was written. The predictions of experts, yeah, the predictions of experts probably vary, but guess what? They're all bad. Okay? It's not that, oh, some say there's nothing. Yeah. Okay, there's a few experts out there who claim nothing's happening, that this is all a figment of your imagination, that's all fake news or something like that. Guess what? That's a very, very small minority and getting smaller all the time. Okay? The more research we've done, the more data we've collected, the more we refined our models, the predictions are getting closer together and actually are getting worse, okay? Meaning that things are happening faster than we ever expected before because our old models weren't as good. They were a bit too conservative. They are worse now, predicting worse now. Now, this statement, that one bothered me. This one really gets my goat. Critical analysis of climate change should be completed before future policies about human-made carbon dioxide are implemented. And my response to this, are you kidding me? Okay, I'm sorry, I get off a bit carried away here. Here's why I say that. When are we going to complete the critical analysis? You know when it's going to be? When it's going to be, yeah, when it's too late. You're absolutely right, when it's too late. Because you never complete. It's always changing. So your analysis is always going to be changing. It's actually speeding up now. It should be slowing down. Now, things like the climate accords, like they did in Paris and then somewhere else, Norway or somewhere else, they've they've slowed some things a little bit, but not enough. Not enough to make any difference. A lot of difference. Okay, you're not never going to complete the analysis, and if you wait until you've completed all your analysis before you may change your policies, it's too late because
Like I said, I think the biggest thing to me is I think about my grandchildren that I haven't even had. Like I don't know what they're gonna do. It makes me nervous. You know what I'm saying? We're like you said, we're headed in the wrong direction, and there's no, not enough efforts to slow this thing down and steer it.
you're absolutely right. I couldn't agree with you more. Okay, and we've got to do something. I mean, if we don't, if we wait till all the critical analysis of the climate change completed, it's too late, baby. It's too late. Uh, it's almost over with by then. So no, we've got to do something now. Now, I wouldn't be surprised if this author hasn't changed his mind since this slide was made, because like I said, this is a fairly old slide based on data that was even older. I can't imagine many intelligent, I hate to say it this way, open-minded scientists who aren't saying, hey, exactly you're saying, we're heading in the wrong direction. And here's the scary thing. All that carbon dioxide we've got up in the air now, that we put over the last 100 years or so, beyond what was normal, guess what? It's going to take us centuries to filter that back out again. Even if we change things right now and stop putting it out there, it's still going to take a long, long time to get us back to where we were, say, 100 years ago, as far as, carbon dioxide levels. So, man, that is a ridiculous statement in my mind. I would have been embarrassed to put it in my book. Okay. Now, that's the last slide. I did want to show you now. Here were some of the things, and this to me there was a picture on the sunspots. Sometimes there's lots of sunspots, sometimes there are very few. Okay, I get it. But that is something that's not that may make, you remember all the jiggle and wiggle it was doing? Yeah, that's going to contribute to that. The trends, though, unless something major is happening on the sun, the trends are not going to be supporting the change we're talking about. Now this, I can't understand this one at all. They've greatly exaggerated the elliptical nature, and they've got us pointing in different directions. That's kind of nuts. And then this one too. The change of our tilt has never been that great that I know of, and I don't think the data support that. I think this is exaggerating things here. This is supposedly illustrating the change of our orbital shape. I don't think there's record of it changing that much. There may be minor changes, but that's not what we're talking about. Okay? Nowhere that. Now, please, folks, on page 597, this is 23-25, there is a case study there on El Nino. This is one of the best case studies, I think, in the entire book. You hear the weather people talk about it periodically. Sometimes they don't mention it, but when it is affecting our weather, they're going to blame a lot of things on it. Well worth a read there. Okay? They talk a little bit about La Nina as well, but not as much. Okay? Then you see Wilhelm Firman Gorenbrnexness or something like that. He's a person in the science now that they feature on. If you're interested in writing on such a difficult name, there's information. However, this is not your source. This is the source of ideas for the paper, but not source of the paper itself. And as you look at that, you'll see that several other people are mentioned there, or at least I think they are. Um, I don't know, maybe not. It's true. Those are names of places. But anyway, there's several potential paper topics there. Now, this is the diagram I was referring to before. This is showing the increase in carbon dioxide levels. This is good recent data. And I don't think you could find anywhere in the world data from the past that showed that sharp an increase in carbon dioxide levels. That's not natural. So why say wait till complete analysis of this is done before you make any policy changes? No, because the policy needs to happen now. And if you'll notice those years that it took such a steep increase, basically from 1960 to 2010 and kept climbing, guess what, folks? That was that same time when, let's go back to that one. Oops, that was it. 1960, did I say, to 2000. That was right here. Look at that increase there. Look at this increase there. Okay? Don't tell me there's no correlation there. That carbon dioxide did not increase in that way into the air in a normal fashion. That was man enhanced, I guarantee. Okay. So, anyway, that's what he says about global warming. I think he's way, way too conservative on this approach. And like I say, he may have changed since then because we've gotten more and better data, all of it pointing to even stronger the effect that we've been having. All right, that does end the chapter. This chapter does have a summary, like all the chapters do. It's a pretty good size summary. And there are some of the key terms. I think the rest of them continue on the next page. A lot of things in the summary, the italicized words and phrases and concepts are there. A lot of those show up in the key terms. The key terms are alphabetical. However, they give the page numbers where they're first introduced or defined. They go on to the next page too, just a few on the next page. Then applying the concepts, the very best thing to study for your test. 45 of those. That's probably a few fewer than normal. The answers are given. Questions for thought, only 14 of those. Again, a few fewer than normal. 4 for further analysis, that's right about normal. And then there's a little invitation to inquiry about microclimate experiments, and you certainly are welcome to take a look at that. I don't know if there's a potential paper topic there, but you might find it interesting anyway. Parallel exercises, those are more like the examples in the book, and those like number 11 and 12, looking at that map like we did, I think those are pretty interesting to look at those. And that pretty much wraps up chapter 23. Are there any questions, issues, concerns, anything that you want to ask before we kind of call it quits today? Especially if there's anything about your research paper, anything about any of the earlier labs, anything about a test that you were confused about. Or now, let me say this. I don't want to call any names, or maybe I need to. One person turned in a test and they answered the first page but didn't answer the second page. And I haven't graded that test yet because I don't want to give you a 50, okay? And I don't know if you know who you are. Excuse me? If it's not you. Wait now. I think you had turned in one with no answers on it, and then you turned it in with the answers on it, so I got that one straightened out. Yeah, I don't know what happened there, but I think you turned in my original, not your answered one, but you did get it taken care of. Right. So if you think that may be the case, go back. No, it wasn't you. It wasn't you. No, it wasn't. does anyone object me calling your name if it was you?
They don't object.
No one's object. Okay,
No.
I'm pretty sure it was Diana. I think. I
Oh, it
can't,
was me?
I don't remember which test it was now, but go back and check your test and make sure that you do you still have them? I mean, yeah,
Yeah, I have all
okay.
my.
Okay, go back and check and make sure that you answered the second page. Especially if
Okay.
it's one that you turned in a while back and you still haven't seen a score for, that's the reason. Okay. And all of you,
Yeah, I know I think I did on one of my tests.
what's that again?
I said, I think I did on one of my tests. I was wondering why, because you graded all of them. One of them, I don't think I
Okay.
but I can see it now.
Okay. Now, if I'm getting as foggy sounding as y'all are, then the internet's bad again. But I'll say this, I'm behind in grading, and I'm even further behind in putting grades on Blackboard. And I'm even behind maybe a week or close to a week in printing off things. So I'm going to try to catch up this evening, this afternoon, evening, as much as I can, but I'm not going to get them all done. But I'm going to be away from the internet this weekend, so I won't be able to enter anything over the weekend. I'm going to have to really bump it this week, this coming week, to try to get caught up. But I'm in the process of doing that. So just because you're not seeing a grade, it may not be your fault. It may be my fault. So um, I did put quite a few grades out in the last couple of days, but I still don't have them all done. Um, Here's another little point. Now, less so in this class than other classes, but a few of you have been really notorious about sending me a lab and even some test with no name on it. Okay, so please try to remember to put your name there. I'm catching most of them. I think I've caught them all for this class because this isn't as bad as some of my classes are, but I swear it gets such a pain for me to print a bunch of stuff and then go back and start sorting it to put it in alphabetical order and then suddenly see no name. I say, well, whose was this? Because I just printed off, 4 or 5 people's stuff, and then I can't remember who all the people were. So please try to remember to put your names. Okay? Like I said, I'm in the habit of checking that before because I'm doing more grading or marking as I print, and that's when I found out. And usually your name's still up there. But occasionally when I've done several at a time, oh no, this one doesn't have a name. My internet connection is unstable. I'm going to quit talking about that until it comes back. Okay, it probably broke up some, didn't it? All right. So, for the rest of the day, I'll answer questions on, if you have any questions about research papers, I'll be glad to answer those. If you have any questions about labs, I'll be glad to answer those. And if you have any questions about tests, I'll be glad to answer those. So it's open mic night, or if you want to just get off and get to work and get caught up with some of the labs or the tests or other things like this, then that's fine too. But let me know how long you want me on here. I'll stay as long as you want me to, but then when I get off, I can get back to grading and printing and grading and entering grades. So let me know. Anybody?
So we got two more labs, right?
Okay, yeah, we're going to do the lab on Tuesday for chapter 23.
Miss Fowler. Miss
Yes,
Fowler.
yes. Can
Okay.
you hear me?
Do anybody know we have two more labs?
Yes, you have 2 more labs. You have chapter 23.
Okay.
Okay, check and see if your mic went off. You can't hear me, so say that. Sorry about that. Okay. It sounds like the communications are getting so bad that I'm about to say, let's go on and end it for the day. What do y'all think? Or can anyone hear me say that? Hello? Angelita, your light's on, but I can't hear a thing.
Okay. Bye bye.
Okay, you're leaving? Okay, bye bye. Um, So I take it y'all are wanting to go for the day. I'm going to stop my sharing. Yeah, I can see we're dropping like flies. So take care. Have a good, safe weekend. I'll be back and we'll see you on Tuesday. Okay? Bye bye.
Bye bye.
Take care.